In section 5.1, we're talking about resolving forces. Now, we have met this idea before. In fact, we've used this idea in the moments chapter. So maybe this is something where after this section you want to go back and have another look at moments and see if it helps some of those questions, if there are any of those that were difficult. But here's the general idea. If I had a force acting this way and a force acting this way, okay, so imagine I've got an object sitting here on the table and I tie a string to it and pull it that way, tie another string to it and pull that way, then what would happen to that object that I've got sitting there? Okay, well, let's imagine it's this dice here, right? And I'll push rather than pulling because I don't have strings to attach. So I'm going to push that way and I'm going to push that way. And what happens to the dice? Well, overall, it moves in this direction here, okay? So if these forces were invisible, let's have a look at another situation. I've got the object sitting here and I have one force acting in that direction. And what happens there? Well, then the dice moves like that. Now, if you couldn't see the forces that were pushing, what would be the difference between those two situations? If you just see the dice moving, well, there wouldn't be a difference, would there? The effect of these two forces and the effect of this one force on its own is the same thing. And we're used to that idea, really, because we know that forces are vectors, and if I do this force, add this force, the resultant force would be this one, right? A force that way plus a force that way is a force that way. So you can think of it as a vector addition. This vector plus this vector makes an overall vector of this one. You know, A plus B is A plus B, and we know that forces are vectors. And we've met before the idea of a resultant force, so if you've got force A and force B added together, the resultant, the sort of net force, is what you get from adding the two vectors together. Now, resolving forces, the idea is going the other way. So if I have a situation where I've got something that I'm pulling along horizontal ground, and it's being pulled by a string attached at this angle, it might be helpful to think of that as one force pulling horizontally and one force going vertically. And that force there could be replaced with this vertical force and this horizontal force. Now, why might that be useful? Well, first of all, we've talked about resolving forces before, but we've only dealt with horizontal and vertical forces pretty much. So if we can think about this as horizontal forces and vertical forces, that'll help us. And secondly, the part of this force here, which is making this object move along the ground, has to happen in this direction, right? Any forces that are going vertically aren't going to move this thing along the ground. So if I have that force there at this angle, the box would move at a different speed to if I had that same force but at this angle. And that's because more of the force for this second version of it here, more of the force is going in this direction. So how much of this force is going in the direction that we're moving in? You know, imagine this is a very heavy box that we're not lifting up from the ground, but we are able to pull along. Well, what's important is what amount of the force that we're putting in is pulling it along. And, you know, obviously if I actually pull exactly horizontally, I'm going to get more luck moving the box than if I pull at a very steep angle like this. Then the box isn't going to move very easily horizontally, is it? So that's the idea. We're going to think of forces, usually forces which are not acting vertically or horizontally, and we're going to think of them as though they are two separate forces, one in the vertical direction, one in the horizontal direction. They could be going up or down or left or right. That's why I say vertical direction. I'm not saying upwards, and horizontal direction, I'm not saying to the right. I'm saying vertically or horizontally. So how does this work? Well, let's take the first example. I've got a force like that, which is at 40 degrees to the horizontal. And I can think of it as though it were two forces horizontally and vertically, like that. So those two forces here that I'm now outlining in red, the resultant effect of having those two forces would be exactly the same as having this one force. So on all the diagrams that I'm dealing with, I can take this force and split it up into those two parts. Okay, now, if I have that, and this is 9 newtons, I'm going to go through this carefully. Again, this is something that we used in the moments chapter, but this particular little method here is one that we will use so many times, and we want to be able to do it really fast. So let's say this is the x component, this is the y component of the force. Well, the x component of the force is adjacent to this angle. So cos of 40 degrees is x over 9. So if I times by 9 on both sides of this equation, I get 9 cos 40 degrees equals x. And that little manoeuvre there is one that we want to be able to do without actually having to go through all the stages. We want to go straight to here. So if I say I've got a 10 Newton force at an angle of 65 degrees, I can think of it as an x component and a y component. The x component of this force is 10 cos 65 degrees because x is adjacent. Cosine is the one that's got an adjacent in it, so it's hypotenuse times cosine of 65 degrees. Let's do the same with y. Sine of 40 degrees is y over 9. So 9 sine 40 equals y. And again, we want to go straight to this line. Let's do it here, straight to this line. 65 degrees, 10 is the hypotenuse. So hypotenuse times sine of 65 gives me the opposite side. Okay? So if I had this force acting horizontally, this force acting vertically, so this one to the right and this one upwards, the result of those two things would be that 9 Newton, the same as that 9 Newton force there. And that's the idea in this chapter. So that's the first idea in this chapter, and that's the idea for the example 1 kinds of questions. And that'll get you most of the way through exercise 5a. But we're also going to start looking at applying this idea to diagrams that are pretty familiar to us already, really, because we saw this sort of thing in the AS mechanics course. So this is 8 kilograms, and it's a box sitting on a table, or a mass sitting on a table. Let's just, I often find it helpful to imagine these as boxes. There's 8g pulling downwards, and there's a normal reaction from the table pulling upwards. And in this case, we have a force pulling this way. Now, a little note here, this box is being modelled as a point. So it doesn't matter whether I put this arrow in this corner, starting at this corner, or starting in the middle, because we're actually imagining that all these forces are acting on one point in the middle. It's sort of quite helpful to still sort of draw a rectangle to imagine the object, but really we should have all these forces acting from the same point because we're modelling the object, the box, as a particle. Now this force in this question is 10 newtons, and it's at an angle of 30 degrees. So, vertically, what's happening? Vertically, we've got forces going up, we've got forces going down. So if I resolve vertically, I get R going upwards, and I also get the vertical component of this force. So what does the vertical component of that force look like? Well, we're imagining this force as two forces, one like that and one like this. Now, this vertical force here, I've drawn it here so that we can see this right angle triangle, but really we'd think of this as a force acting horizontally and a force acting vertically. Oh, yeah, that's too high, isn't it? There we go. This and this are supposed to be the same, right? So this vertical force is actually acting on the parcel, isn't it? So you've got R and this bit acting upwards. You've got 8 acting downwards, and you've got this bit acting horizontally. I've drawn that force, though, over here so that I can see the right angle triangle, and that makes it easier for me to picture and get the right expression for this force. So what's this force here? Well, it's 30 degrees. So, well, 10 is the hypotenuse, 30 degrees is the angle, and I want the side which is opposite, so that is sine 30. So R plus 10 sine 30 equals 8g. Okay? That's resolving vertically. If I go horizontally, well, actually, there's nothing pulling it to the left, is there, when I look at this? So what's happening horizontally is that I've got a force going that way, and that is not balanced out by anything going this way. So vertically we're in equilibrium, the forces are balancing. Horizontally we are not in equilibrium, we have a resultant force. So horizontally I'm going to apply F equals ma, and the resultant force is 10 cos 30 degrees, and that is equal to the mass, which is 8, times the acceleration, which is a. And R resultant force is a vector, and A acceleration is a vector, so I should have underlined those really. Now, those are the two things we can do with a situation like this. Very similar to the moments chapter again, that in the moments chapter you could resolve forces and balance out the forces vertically and horizontally, and you can take moments. Well, in a question like this, you can work out the vertical components and the horizontal components. If the thing is in equilibrium in that direction, so vertically this object is not accelerating, it's not accelerating off the table, and it's not accelerating down through the table, so therefore upwards forces equal downwards forces. Horizontally, it is accelerating, so it's basically the same trick as balancing out the forces, but we're just finding the resultant force, F, and putting that equal to mass times acceleration. So the difference between balancing the forces out, resolving them, and applying F equals ma is only really at the very last minute. The difficult bit is making sure you've got all the forces written down nicely. Now, in example 3, there is another way of doing this. I think this is more really sort of academic interest. It ties in with our understanding of vectors, and very occasionally this is a useful way of thinking about these things. What we've got is a particle here with P going in this direction and Q going in this direction. So two different forces, P and Q, at an angle of 45 degrees and 30 degrees. Now, if we want to know the resultant force, because these are vectors, the resultant is like the resultant vector, right? So it's Q goes at 30 degrees to the horizontal in that far. What does it say? Q's got a magnitude of 8, so length of 8 at 30 degrees. P goes at 45 degrees. So if that's 45 degrees there, this is also 45 degrees here. And that's P, and P has a magnitude of 10. So those two vectors, 8 that way and 10 degrees that 10 newtons that way, have a resultant force. Well, Q plus P results in this force here, which I'll call R for resultant. Okay, and I can work out R by working out the various angles and things. Now, the diagram in the book is a little bit better than my one's turned out, but I can put them there as a triangle. So this is often called the triangle of forces method, and the reason it's called the triangle of forces method is because with the forces make a triangle, first of all, if the thing is in equilibrium. Sorry, it's not in equilibrium, is it? We've got P and we've got Q. R is the resultant. So there's three forces involved, so the three forces come together to make a triangle. If I had more than two forces, if I had more than P and Q, then I have P and Q and another one, then we'd end up with a whole sort of polygon. And if we end up with more than a sort of triangle, then it gets sort of too complicated to deal with. So we call it a triangle of forces because if you've got more than three forces involved, P and Q and the resultant, then it's too it's often too fiddly a method to use. Even frankly, with the triangle of forces, we don't tend to use that method of doing it, but we could. Can you see the idea? We've got all the information that we need. That angle there was 45, and that's going to lead us to having the 105 degree angle there, because let me just sketch this out in case you can't see this one. Totally reasonable if you can't really. There we go. My diagram looks a little bit better now. We've got 30 degrees there, therefore we've got 30 degrees here. We've got 45 degrees here. That leaves this angle in the middle to be 105 degrees. So if I know that's 105 degrees, I know that that's 30 degrees, I'm trying to work out this angle, and I'm trying to work out the length of this thing here. So by all the properties of triangles, I can get there, right? Now, maybe I'm going to have to do some things like there's a horizontal line there, there's a horizontal line there, so I can work out, you know, that this angle on 45 degrees have to add up to 180. I've worked out this 105 degree angle here, and you know, we're going to have to mess around a little bit with the geometry of it, but the idea of the triangle of forces is that we just use the properties of the triangle. Now, the other way of going about this, and the one that I suspect everybody's really going to use, unless they force us in that direction in the exam, is just to do it this way. The resultant force, well, vertically, I've got, what did it say? P was 10, wasn't it? And Q was 8. Vertically, what have I got going on? 10 sine 45 degrees, take away 8 sine 30 degrees. So the vertical component of the resultant force is that. Horizontally, I've got 10 cos 45 degrees, oops, pulling to the right, and we've got 8 cos 30 degrees. pulling to the right as well. So the vertical component is that, the horizontal component is that, so I suppose we should have written this one first. We should have the horizontal component first, shouldn't we? But from those two components, I can then work out what the resultant force is, because it's like me just coming into here and telling you this distance and this distance. If you know that distance and that distance, it's no trouble to work out this length and this angle, is it? Okay, so that is everything in the first section. Example 4 is just using the same techniques there. I don't think we need to go through that one separately. Good luck with section 5.1.